This is Unit 6, Periodic Table, Part 1 Notes. By the end of this unit, you should be able to explain the use of chemical and physical properties in the historical development of the periodic table. You should also be able to use the periodic table to identify and explain the properties of chemical families. So before the elements were placed in order on a periodic table, scientists or early chemists used the chemical and physical properties of elements and sorted them into different groups. That was based on properties such like chemical reactivity, and they only figured out those properties by using them in experiments. However, the first scientist that was credited with organizing the elements in some sort of ordered fashion was Mendeleev. Mendeleev arranged the elements according to atomic mass. And again, mass would be the proton number plus the neutron number. And later on, it was figured out, or isotopes were discovered, which are the same element, but with different numbers of neutrons. So you could potentially have the same element and have different neutron numbers, which meant you had different masses, and that confused everybody because they were not in that correct order, or different masses could lead to different types of elements. So then Moseley was the second scientist that reordered the periodic table according to the atomic number, which is the proton number. And this is the modern periodic table that we know of today because the elements are listed in increasing atomic number, which also represents the proton number. And if you change the proton, you change the identity of the element. So this is the periodic table that we use today. So the periodic table is just a table that, again, displays the elements in order of increasing atomic number, which then organizes them according to different chemical properties. And based on where the elements are, we can identify specific chemical and physical properties that we can use to describe the elements in the periodic table. We need to know the difference between what a period is and what a group is. Periods are the rows on the periodic table, and the properties change going from left to right. So the periods are going to go across the periodic table. And if you look at the table, there are 7 different rows or 7 periods that go across the periodic table. So when I'm talking about periods 1, periods 2, periods 3, periods 4, you're looking at the elements starting from the left side and all the way to the right side. As compared to the groups. The groups are the vertical columns. These are also known as families. And within your family, you share similar characteristics. Just like all the elements in group, or the last group on the periodic table, they're all considered noble gases, and they all share the same property of being unreactive. So whenever we're talking about groups, there are specific groups that we will label later on. But I wanted to just clarify, whenever I'm speaking about the A representative groups, I am talking about groups 1 and 2, and then we have the 3A, 4A, 5A, 6A, 7A, and 8A. So those are our A representative groups, while the middle section here, these are your B groups, or your transition metals. And we don't necessarily talk about the B section very much, but I wanted you guys, even the ones down here, those are all your transition metals, which we'll label here in a second. So when I refer to the A groups, you need to look at the 1, 2, and then 3 through 8 columns, and then the B non-representative groups. Those are the transition metals. And they share similar characteristics within the same group or family. And then just to reiterate, you have different chemical reactivity across the period. Okay, so you should also be able to identify where the metals, metalloids, and nonmetals are on the periodic table. And you can separate everything based on the metalloid belt that starts at boron, and it goes stepwise down all the way to the bottom of the periodic table. So the metals are all to the left of that metalloid belt, except for hydrogen. Hydrogen is the exception. The only reason why hydrogen is placed in group number 1 is because of its reactivity and the fact that it has one valence electron. And if you are touching this belt here, you are considered a metalloid. Then everything to the right of that metalloid belt are your nonmetals. And all three groups have different types of characteristics, such as metals are very lustrous or shiny. They are good conductors of electricity, heat, or energy. They're malleable and they are ductile. Malleable means you can mold them, and then ductile means you can run them in through a wire. Nonmetals, on the other hand, they can be gases at room temperature, and then you can also have some solids. These are your solids down here. More or less your gases are in the upper right-hand corner. But the gases, there can be gases at room temperature, but the solids are usually brittle, and they're very poor conductors of electricity. And if you are touching this metalloid belt, such as the metalloids, you have shared characteristics between metals and nonmetals. So depending on the element, you can either be a good conductor or you could be a poor conductor. So they're going to be shared, and it can, depending on the element, they can have either or. So they're just like a mix of a metal and a nonmetal together. But what you do need to memorize is that metals are all to the left of the metalloid belt. The metalloids touch this metalloid belt line, and then your nonmetals are to the right. So a couple of families that you need to be able to identify are the groups 1A, 2A, 7A, 8A, and then groups 1 through 8B. And previously I mentioned the A versus the B group. And just to clarify again, the A groups 1 and 2, then you have 3, 4, 5, 6, 7, and 8. And I know it says 13 through 18, but that is 3A through 8A. So those are your A representative groups. Then your B's are your 3 through 12 here, or this is your 1 through 8B. And this is your transition metal section, and that's even considering the lanthanides and actinides. Okay, so those are your transition metals. Group 1, these are known as your alkali metals. So these is just alkali metal groups. Anytime I mention an alkali metal, you need to go to group number 1A. And then your group 2A, these are your alkaline earth metals. And if you can't read my handwriting, they're written over here in the data table, or the legend. But it's alkaline earth metals. And the easiest way to remember groups 1 and 2, alkali, that's one word, so it's in group 1A. Alkaline earth, two words, so it's in group 2A. You also need to know where the halogens are. That's group 7A. Halogens, the reason why they're called halogens, they have 7 electrons around their valence shell, so it looks like a little halo. But those are your halogens in group 7A. And then group 8A, that's the last group here. These are your noble gases. And then your groups 1 through 8B, these are your transition metals. That's where your transition metals are, pretty much in the middle of the periodic table. So again, alkali metal, that's group number 1. Alkaline earth metals, group 2. Halogens are group number 7. And then your noble gases are in group number 8. So because the elements are arranged in a very specific way according to atomic number or proton number, we can identify different properties or characteristics of these elements. For example, the valence electrons, we've already talked about these, but these are the electrons in the outermost shell, and it's determined by the group number. So if you were to go back to groups 1A, groups 2A, 3A, 4, 5, 6, 7, 8, those group numbers for your A representative elements only, those group numbers tell you the number of valence electrons. So your group number is equal to the valence electrons. So group 1, there's 1 valence electron. Group 2 has 2 valence electrons. Group 3 has 3, 4 has 4, and all the way through. So group number 8 has 8 valence electrons. That means it has 8 dots in the outermost shell of that specific element. So looking at the group number, you can determine the number of valence electrons. And because elements in the same group have similar characteristics based on reactivity, that is due to the valence electrons. So the shared reactivity of your elements in the same group is going to be based on the valence electron number. And that's an important thing that you have to remember, because the elements within the same group, they react the same because they have the same number of valence electrons. That's because valence electrons has a lot to do with the chemical reactivity of those elements. Okay, so going into these second two rules, we have this octet rule. That's because all elements want to have 8 electrons in the outermost shell. Once an atom has 8 electrons, it becomes completely stable and unreactive. And that can be related to group number 8. Because they're in group 8, these noble gases have 8 valence electrons. And hopefully you remember back from your previous years that the noble gases are the most unreactive group because they have a full octet. They have all 8 electrons. They are unreactive. They don't want any more. They don't want to give any less. So whenever you have 8 electrons, you are unreactive and are completely stable. The only exception to that rule is called the duet rule. That's because hydrogen and helium are on period number 1. So that's row 1. Hydrogen has an atomic number of 1. Helium has an atomic number of 2. So on the first ring, you can only have 2 valence electrons. They cannot have any more than that because their atom physically cannot hold any more of those electrons. So once the first row is filled up with 2 electrons, we draw the second ring or the second shell, like in our Bohr diagram, and we move on to adding those 8 electrons there afterwards. But once you fill up that first ring with 2 electrons, those 2 atoms are completely stable. That is called the duet rule. So it's similar to every other element whenever they fill up those 8 electrons. Once hydrogen and helium have 2 electrons in their outermost shell, they are completely stable and unreactive. And that is why helium, even though it has 2 valence electrons, is placed in this last column because it shares similar reactivity characteristics with all the rest of the noble gases. Okay, so groups can tell you the number of valence electrons, and periods will tell you how many shells are around the ring. So if you're in period number 1, you have 1 shell. Period 2, you have 2 shells. Go down to period, 5? You have 1, 2, 3, 4, 5. So your periods or your period numbers will tell you the number of shells that go around the nucleus. And that's just a little bit of extra information that you should write down in your notes as well, because that'll be important for the trends later on. Okay, and then going to your charges here, we need to know the charges of the group A representative elements as well. So not only should we know the valence electron number based on the group number, we can determine what their charge is based on becoming unreactive or getting close to the noble gases or having 8 valence electrons around their shell. So charges are also known as oxidation numbers, and it's based on losing or gaining electrons to become stable. So they want to mimic the closest noble gas atomic number-wise, not location-wise, but atomic number-wise. And just to review, cations are going to lose electrons to form positive charges. Those are all the metals. So anything to the left of that metalloid belt, they will lose electrons to become cations. While anything to the right, they're going to gain electrons to form negative charges. Because electrons are negative, if you gain something negative, you become a negative charge. Okay, so those are your non-metals. So looking at group number 1, there's 1 valence electron. Okay, hydrogen and everything else down here all have 1 valence electron. So you need to figure out, okay, well, for example, let's take sodium. If you have 1 valence electron in the outermost shell, which there are There should be 3, so let me redraw that real quick. So if hydrogen, lithium, sodium. Sodium is on period number 3, 1, 2, 3, with 1 valence electron in the outermost shell. So here's a question. Is it easier for sodium to lose this 1 electron or to gain 7 more to fill up that shell? Well, you want to do as least as possible because no one wants to do more work than they have to. So it's easier for sodium to lose that 1 electron to become a +1 charge. If it loses that 1 electron, it now has 10, which is mimicking neon. Otherwise, it could gain 7 to try to mimic argon, but that's way too far and way too much work for that element. So group 1 forms +1 charges. Same thing. For magnesium, we have 3 rings with 2 electrons. So is it easier to lose these 2 electrons or to gain 6 more? Well, you want to do the least amount of work possible. So you could lose those 2, become a +2 charge because you're getting rid of electrons, to mimic, again, neon. Otherwise, gaining 6, it would try to mimic argon, and that's way too far away. So going on to the group number 3, again, it's easier to lose 3 electrons than gain 5, so it's going to form a +3 charge. So now we get to carbon, where there's 4 valence electrons. So you could either lose 4 or you could gain 4. Okay, well, it can actually do both. So group 4 is going to form they can form a ±4 charge. Let me rewrite this. So we have +3, ±4, because you could gain 4 as easily as you can lose 4. So then nitrogen, these all have 5 valence electrons because they're in group number 5. So it's easier to gain 3 electrons than to lose 5. So gaining 3 negative particles, you form a -3 charge. Elements in group number 6, it's easier to gain 2 electrons to act like neon, so they're going to gain -2. And then the fluorine is right next to neon, group 7, so it's easier to gain 1 electron, so it's going to form that -1 charge. Okay, and the easiest way to remember the charges of the group 8 elements, we go back to your noble gases. They already have 8. They don't want to gain or lose anything, so they're actually neutral, and they don't add or gain electrons. But to form the charges of the group A elements, you could just climb the mountain, where you have your +1, +2, +3, ±4, -3, -2, -1. And all you have to do is say group 1 form +1 charges, group 2 forms +2, group 3 forms a +3, group 4 is ±4, group 5 -3, group 6 is -2, and then group 7 is -1. So I know this is a lot of information to have written down in your ISN, but you can print this periodic table out or you can draw a mock periodic table, but you need to be able to label all the periods, label all the groups, and then identify your charges. All right, so are you able to explain the use of chemical and physical properties in the historical development of the periodic table? And are you able to use the periodic table to identify and explain the properties of chemical families? If you're not able to answer these questions, then you need to go and rewatch the video or ask questions during the lecture. We're also going to practice everything that we've talked about. We're going to be labeling a periodic table, and then we're going to be working some problems, identifying valence electrons, charges, location on the periodic table, and using that information going into the periodic trends on the next lecture that you watch.